Alright, now we're going to go back to where we had left off from the last video, looking at applications of exponential growth and decay. And the first one up here has to do with population. It says on January 1st of the year 2000, the population in Texas was approximately 21 million people. Okay, 10 years later, the population was 25.2 million people. Write a function in the form P of t equals P sub 0 e to the kt to represent the population P of t of Texas t years after 1/1 of 2000, and then we're going to round k to 5 decimal places. So what we need to do is we need to be able to find our variables are going to be P of t and t. We need to find P sub 0 and k. Well, they give us P sub 0 is 21 million. So what I'm going to do is I'm going to write this in terms of millions, and I'm going to write this as P of t is equal to 21 for the 21 million e to the kt. Now it says here that in 10 years, when t is 10, the population is 25.2 million. So that would mean that P of 10, which would be 21e to the k times 10, would equal 25.2 million. So now I have an equation in which I'm going to be able to solve for k. I'm going to divide both sides by 21. I have e to the 10k is equal to 25.2 divided by 21. I don't know what that is, a little bit more than 1.2 somewhere. Wait a minute, maybe it's 1.2. Goes in 1.2. Oh, nice. So that one came out nice and neat. And then I'm going to take the natural log of both sides. I'm going to use my property of logarithms and bring the power out in front. One of the laws of logarithms, I get 10 k. Well, actually, in fact, because this is a natural log and this is e, this just equals 10k. I don't even have to worry about rewriting because the natural log of e is just 1. And then I'm going to divide both sides by 10, and I get the natural log of 1.2 divided by 10, which is approximately 0.01823. 1, 2, 3, 4, 5 decimal places, just like they asked for. So now my actual answer is, I'm not done because they want to write the function. My function P of t is equal to 21 e to the 0.01823 t. And that's the answer for part A. Then it says in part B, we're going to use this and we're going to predict the temperature on predict the population on 1/120. And we're going to round to 1 decimal place. So I'm going to plug in for t 20, right? Because this is 20 years after the initial time of January 1st, 2000. So t is 20, and that's going to give me P of 20 is equal to 21 e to the 0.01823 times 20. So of course I'm going to multiply here, e to that power times 21. And if I've done this right, and hopefully I have, I'm going to end up with 30.2 to 1 decimal place. There's a decimal point right there. So that means that the population of Texas on 1/120 should be 30.2 million. Okay, hopefully you can read that all right. My handwriting's a little sloppy here. Now, I'm going to go back to part A. It says from the function, or use the function in part A to determine what year the population of Texas will reach 40 million if the trend continues. So I come back to here. P of t is equal to 21 e to the 0.01823 t. And this time I'm trying to figure out the year because P of t is going to be 40 million. So I'm going to put a 40 here. I'm going to divide both sides by 21. And I'm going to flip-flop the sides. I'm going to get e to the 0.01823t is equal to 40 21st. Almost 2, but not quite. I'm going to take the natural log of both sides to get my exponent where I can get at it. And I'm going to get 0.01823t is equal to the natural log of 40 21st. I'm going to divide both sides now by 0.01823. Definitely need Mr. Calculator close by. And I get, let's bring it up here, I get t is equal to, this is going to be approximate, I don't know, we can kind of round this one off, but if I'm not mistaken, this turns out to be 35.3. Now remember, t is the number of years, so it's 35 years and some change, a little bit beyond that, 3/10 of a year. So if we started in the year 2000, so the state of Texas will reach a population of 40 million in the year 2035. And that would be my answer there. Now I have a tendency to do this. I put a nice problem down here that involves Newton's law of cooling, and I forgot to mark that it is a review problem from the semester exam review. Now, there were some problems involving Newton's law of cooling that were in a previous section in the assignment, but I don't think we spent any time really looking at one in one of the videos, so we'll do so now. Use Newton's law of cooling to solve the following problem. A dish of lasagna baked at 350 degrees Fahrenheit is taken out of the oven into a kitchen that is 74 degrees Fahrenheit. After 7 minutes, it's been cooling for 7 minutes, the temperature of the lasagna is down to 290 degrees Fahrenheit. What will the temperature be in 14 minutes after it's been taken out of the oven? Now you say, wow, that's easy. It dropped 60. In 7 minutes, it'll drop another 60. No, not necessarily. This is the equation that we're going to use. This is going to be our temperature. This is the temperature of, how do I want to put it, not the atmosphere. I know I have an A there, but in this case, it's 74 degrees, the temperature of the surrounding environment. This is your initial temperature, so for us, the lasagna baked at 350, so that'll be 350, and again, the outside environment. T is your time here, and this will be in minutes, and we're going to have to figure out what K is on top of all this before we can even come up with an answer, kind of like we did back here in this problem. So let's plug in what we know and see if we can figure this out. I know that the temperature here is 74 degrees. The temperature here is 350 minus 74 degrees, e to the opposite of k, t, but we know that after 7 minutes, when t is 7, that the temperature is 290. So I can plug that in and I can find k. So I am going to subtract 74 from both sides and subtract that here in just a second. So I get 216 is equal to, what's that going to be, 276? Did I get that right? 276 e to the, I'm going to write this as negative 7k. I'm going to divide both sides by 276. I don't know what that's going to be right off the top of my head. I'm going to have to grab a calculator. I'm going to take the natural log of both sides. I've been doing that a lot on these problems. And then that's going to give me negative 7k is equal to the natural log of this fraction. And then I'm going to divide both sides by negative 7. So I have the natural log of 216 over 276 divided by negative 7. And that is what actually goes here. Now we have a negative in front, although it's kind of difficult to see there. That's a negative in front. So let's see what happens here. Now, if I go back and figure out the temperature in 14 minutes, that would be T of 14 is equal to 74 plus, now I already know what this is. This turned out to be 276 to the times E to the KT, to the opposite of KT. So it would be the opposite of this. That'll just make that positive. So I'm going to write this as 1/7 the natural log of 216 all over 276 times T, and this is 14 times 14. Well, the 1/7 and the 14, right? That just becomes 2. So that's going to be 2 times this natural log here. And now it's time to grab my calculator. And if I do this, and if I grab my calculator, this turns out to be 243.04. So since it's so close to 243 and it didn't give us a value in which to approximate this to in the directions, I'm going to say that the temperature of the lasagna will be 243 degrees Fahrenheit after 14 minutes out of the oven. Okay, I should probably circle that or something there so you can see that that's the answer. That's an interesting little problem. It's something you'll see, again, Newton's law of cooling, you'll see that in physics and you'll see that in calculus.